right, welcome to Mr. Strauss's Chemistry Class, Season 2. Better than Downtown Abbey.
What is that?
When we last left off, we were wondering, is the electron a particle or is it a wave? And we were going to find out that cliffhanger.
It's a wave.
So, according to the single slit and double slit experiment, the electron does behave like a wave, so it appears as if the electron is both wave and particle. So if a particle can act like a wave, then that should be for all particles, not just one particle. If the laws of physics are going to exist, they exist for all things, not just for certain things. So DeBrogllie said that if particles can behave like waves, then particles should have wavelengths and frequencies. At the same time, Einstein was studying matter and energy, and under classical theory we said that matter and energy are two separate categories. You got matter, which is particles, solid, and waves are composed of energy. They're not solid. You can't touch a light wave, you can't touch a sound wave. It's everywhere. But under quantum mechanics, we begin to see that, well, maybe they're not two separate categories. Rather, matter and energy are different forms of each other. You can turn matter into energy, and you can turn energy into matter. And Einstein related these two in his famous equation E equals mc squared. That's for later. So, in this equation, mass is in kilograms, and c is the speed of light. So let's just do a little equation here. Let's do a little example. Suppose we take Ryan, and Ryan weighs about 75 kilograms. And we throw Ryan into a nuclear reactor, and we convert him into energy. How much energy would be produced if we turned Ryan into energy? So 75 kilograms times 3.00 times 10 to the 8th meters per second. Square it.
Someone's supposed to do that.
I am going to do it. Should be about...
You just did that.
something to the 16th power. Oh well. 6.8 times 10 to the 18th.
Close.
Now what are the units on energy?
Kilojoules per mole.
Could be kilojoules per mole, but are we dealing with a mole of Ryans? No, just one Ryan. So it would be joules. That's what we measure energy in. Now, you don't need to know this for our course here, Marissa, but it is helpful to know in any science course. Kilograms times meters per second but the meters per second were squared, right? So it becomes meters squared over seconds squared. 1 kilogram meters squared over seconds squared is equal to a joule. So if you're ever wondering how the units cancel, That's how they cancel. Now, is this a lot of energy?
Yeah. No.
It's kind of hard to put into perspective. So let's try to maybe do a little more math here to see how much energy this is.
It's like 6 billion energies.
Yeah, but you know, how fast do we use the energy is the question. Like, I mean, what can we? So a 75 watt light bulb
Uses 75 watts.
uses 75 joules every second.
Okay.
A 100 watt light bulb uses 100 joules every second.
So that's not a lot of energy.
And that's why they want to move towards the compact, you know, fluorescents, because they use like 12 joules every second. They're like 12 watt bulbs. So a 75 watt bulb is 75 joules every second. So if we take 6.8 times 10 to the 18th joules, how long could we power a 75 watt light bulb?
Divided by 78. Or
So 75 joules every second. And let's turn that into years. Here's 3.16 times 10 to the 7th seconds in 1 year.
How do you know that?
Because I memorized it. And if you calculate that out, it comes out to be 2.8 times 10 to the 9th years. So in other words, if we throw Ryan into a nuclear reactor, we could power a 75 watt light bulb for 2.8 billion years.
That's a lot of energy.
That's a lot of energy. Do you think it's worth it?
Yes.
I think so. You ready to take one for the team, Ryan?
Think about if you threw a whole classroom of students.
Not to worry, Ryan. You can't throw just anything into a nuclear reactor. You have to throw unstable atoms into a nuclear reactor.
What happens if you throw?
So the atoms we destroy are not Ryan's atoms. We destroy uranium, plutonium. So don't worry. You can't actually do this. Yeah.
What happens if you throw stable atoms in there?
You have to put more energy in to kind of start the process of breaking them apart. So you want to start with something unstable already. You know that analogy that I gave you? We all have a breaking point, okay? We all have a breaking point. So eventually anybody can have a nervous breakdown, but some of us can take on more. So if you want to have someone have a nervous breakdown, start with someone who's already, you know, unstable. Then it's only just a little push and they just melt and fall apart. So you can, yeah, so enough said. Any questions on this calculation? Okay, now back to DeBrogllie. If matter can be converted into energy and energy can be converted into matter, we should be able to relate the two. So a nuclear reactor turns matter into energy. A particle accelerator can convert energy into mass, but you can't make a lot of mass, Colin. You know, it's not like, you know, all of a sudden there's like 15 pounds of gold that they just made out of thin air. You can't create much mass from those particle accelerators, but you can. So if this is the equation for energy of a wave, then this is the equation for the energy of a particle. And waves and particles are different forms of each other as well. we should be able to set these two equations equal to each other.
They should equal each other.
So hc over lambda is equal to E, which is equal to mc squared. So hc over lambda is equal to mc squared. Let's solve for lambda. So hc is equal to mc squared lambda.
So HC.
Divide both sides by mc squared. That c cancels with that c, or one of them. So I end up with hmc is equal to lambda. So this is the equation for the wavelength of a particle.
Can you do how many particles are in a wavelength? Same thing. Never mind. Keep going.
Yeah, you can find the wavelength of a particle
How?
through this equation. Now c, that's the speed of light, right? Only light can travel the speed of light. So, but it's a speed. I'm going to replace c with v, velocity. And it's basically the same thing. The speed of light is a speed, v stands for speed. I'm just replacing with h over mv because particles can travel at different speeds. Light only travels at the speed of light.
So that equation's for anything?
That equation is for, it can be used for anything, yes,
Or you only usually use it for a particle?
but only usually for a particle.
A single particle?
You can either do it for a single particle or a mole of them, doesn't matter. So let's do an example here. What do you say, Pat?
Sounds good.
When Pat is skating around the hockey rink, his velocity is probably somewhere on the order of, let's just say 9.0 meters per second.
Is that fast?
That's fast, but he is on ice. His mass, 75 kilograms. So let's calculate Pat's wavelength. So Planck's constant goes on top. How many Pats are we dealing with here, Jordan? Are we dealing with one Pat or a mole of Pats? One Pat. So it's going to be 6.626 times 10 to the negative 34th joules seconds per one Pat.
Wait, where'd you get those 6 points?
Planck's constant.
Oh, yeah.
How can you put one pad on the bottom instead of?
Because Planck's constant in this form is joules times seconds per one particle. Particle stands for anything that has mass. So it could be per one electron, per one banana, per one table, per one Pat.
Is it 34 or 24?
34. We've got the mass. The mass must be in kilograms
The bottom's 675.
times the velocity, 9.0 meters per second.
675.
And I get 9.8 with 2 sig figs times 10 to the negative 37th. What do we measure wavelength in? meters. So 9.8 times 10 to the negative 37th meters. Yep, Mackenzie.
So, if you're doing meters, wouldn't you do kilograms on top, or the 3.991?
No, because the joule, remember this is where I said you don't have to know it for this class, but it's helpful. A joule is a kilogram meters squared over seconds squared. So if I were to replace the joule with that unit, you'd have, you don't need to write this down, but if I replace the joule seconds with that, you'd get kilograms meters squared over seconds squared times seconds divided by kilograms meters per second. So then the seconds and those seconds cancel, the meters cancel with one of those meters, the kilogram cancels, and I'm left with 1 meter left. That's how the units cancel. But it might be just easier for you all, for our southern friends, to just remember that wavelength is in meters. All right, all y'all? I'm fixing to do another problem. How about you? I'm going to get some dislikes on my website. All right.
YOLO.
Yeah. So, Pat's radius. Pat's radius is probably about 0.3 meters. So, Pat's radius is 0.3 meters, and his wavelength is 9.8 times 10 to the negative 37. Remember, particles can be like waves, waves can be like particles. I know this is kind of strange to imagine, but Pat has a wavelength. The wavelength is the distance between two peaks. So what does that mean about Pat? Does that mean he's like vibrating back and forth, going like this?
No, with the particles are moving.
Okay. Well, actually, Pat does have a vibration to him. He does have a wavelength. He does have a frequency. However, how big is that wavelength compared to his size?
Small.
Very, 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 very small. Okay? So the fact that Pat has a wavelength and a frequency, it doesn't matter. Okay? It's like saying, you know, if the space shuttle is going up into the sky, it doesn't matter if a fly lands on it. No. Okay? So when we see Pat skating around on the hockey rink, he looks clear to us. We know where he is. He's not like vibrating all over the place. But let me give you an analogy as to what would happen if his wavelength was big compared to his size. So here's a tuning fork. Okay?
All those things are sick.
It's nice and clear, right?
Yep.
Okay? Now, I'm going to give it a wavelength big compared to its size. Now, does it look clear?
Not really. It's like fuzzy.
Does it look a little blurry?
Isn't that like a medical tool? I swear to God it is. There's one like that and you're like, yeah. Yeah.
Oh, it does.
No, I promise. There's something like that and it,
That's totally fine.
yes.
Manufacturers in here.
See,
It
I was
is.
right.
Yeah.
I hate all you guys. I knew it had something to do with a broken bone. See, here's the thing, I'm just smarter than all, so that's why you're present. I know.
It's like a white guy. Like a
Yeah.
dirty white guy.
Yeah.
So, if you have a large wavelength compared to your size, it is going to look a little bit blurry to you. So let's redo the same calculation, but this time with an electron. So the mass of the electron is 9.1 times 10 to the negative 31st kilograms. Be aware that if you look that mass up, they'll give you the mass in grams. Convert it to kilograms. So 10 to the negative 28th in grams, but you got to convert it to kilograms, so it's to the negative 31st. Velocity. Electrons travel very fast. Close to the speed of light. Not the speed of light.
So
only
2.99.
That's pretty much as fast as you can get them to go. I'm going to just say
0.03
times 10 to the 8th, just because I don't feel like dealing with 2.99.
You want a challenge?
Calculate the wavelength. Are we dealing with one electron or a mole of electrons?
One electron.
One electron, so it's 6.626 times 10 to the negative 34th joules seconds per one electron. We have our mass. We calculate the wavelength. It comes out to be
3.6 negative 12.
Now, what is the radius of the electron? The best estimates of the radius of the electron is about 1 times 10 to the negative 13th meters.
So that's a lot of energy. It's a lot of wavelength. That's a large wavelength.
So compare the wavelength to the size of the object. Which is bigger, the wavelength or the object?
The wavelength.
The wavelength. Completely opposite of what Pat is. Pat, his wavelength was extremely small compared to his size. But here, the wavelength is actually bigger than the object itself. So even though the electron has mass, if you tried to look at it, if you could look at it, what would it look like?
Vibration.
It'd look blurry. Okay? You wouldn't be able to pinpoint, there it is, because it's blurred or smeared out over space. Okay? If Pat had a very large wavelength, we wouldn't be able to figure out where he was on the hockey rink. He'd be kind of smeared out over every place. He'd look blurry. He'd be like, is he there? Is he there? Couldn't tell. So the way we look at this is that the electron is everywhere because it's a wave, and a wave spreads out. So the electron is everywhere, and it's also somewhere. I know this gets pretty darn confusing, but again, it's kind of like that little picture that I showed you yesterday. If you want to see the old lady, it's an old lady. If you want to see the young woman, it's a young woman.
Yeah, we didn't have.
When you want to see the what?
It was Sunday yesterday.
You never saw the pictures yesterday?
No.
It was not 2 days ago.
Well, not 2 days ago.
No, we didn't see the pictures.
I showed you the pictures
No,
of the
we-
old lady. and the
Yeah,
young
we
woman.
did.
Yeah, we did.
Why didn't I see them?
Because there was an old lady and then a girl turning away was the young lady.
Yeah.
And I didn't see the young lady until the end.
I didn't see
I
one.
could
I never
see
saw the
old lady.
pictures.
Let me show you the pictures again.
See what she did.
Just because it's a little.
No, I'm actually getting.
It's a little
because I wanted to
appropriate
see
right now.
It's important to see this.
So
I don't see the.
I don't see the old lady.
How do you not see the old lady?
The old lady's
Oh, I
first
see.
thing.
If you want
I see the young lady.
to see the electron as a wave, then the electron will be everywhere. If you want to see the electron as a particle, then it will exist in one location.
Where's the young lady?
Where's the old
I
lady?
see the old lady turned away. Where's the young lady?
No,
The
the
old
young
lady's
lady.
not turned away.
The young lady is turned over.
The whole
So
picture
where's
is
the old lady?
Okay, I see the old lady, but it like keeps going out.
I don't see it. I'm lost. Can I see that slide?
Oh, I see.
Where is
It
it?
should, like, there should be another.
Show me the old lady.
It's the whole
The old lady's the whole picture.
See, that's like her coat and stuff. Then her nose is right in the middle. Her chin is under her nose.
Okay,
This
so
is the young lady.
Yeah, and that's the nose of the old lady.
what does this mean then in terms of the nature of the electron in quantum mechanics? That brings us to
Holy.
Werner Heisenberg and the uncertainty principle.
I see the old lady now.
That's great.
Holy, that was cool.
So it is very easy to determine the position of large particles. Example, pad on hockey skates. We know where pad is.
We see him.
So we would say that in a large particle like a baseball, the position is determinate and the uncertainty is very low.
Is that when it's just sitting there or when it's...
Even when it's moving. You know,
Yeah, you can still see
Pat on hockey skates, he's going close to 20 miles an hour. 9 meters per second. But we still know where Pat is. It's not like he's a blur out there and we can't locate him. So we would say that the position is determinate, the uncertainty is very, very, very low. Why? Because the wavelength is small compared to the size. So if I wanted to measure the position and speed of that baseball, I get out my radar gun.
Here's the person. Where's the other arm?
It sends out a radar wave. Here's my baseball. When the radar wave hits the baseball, the radar wave will bounce off the baseball. And does anything happen to the baseball? No. The baseball continues to travel in a straight path. So I can measure the position and the speed of a baseball using a radar gun. The police can use a radar gun to measure your position and speed too as you're traveling down the interstate.
Can they be moving?
Pardon?
Can they get your speed when they're moving?
Can they get your speed while you're moving?
Yeah, when they're moving. Like, if you're going one way, they're going the other way. Can they call
Yeah, oh
It
yeah,
has to
they
be
can
like
get it too.
perfect though.
Yeah. No, they can do it.
They
It's
have to focus right on the license plate.
it's more accurate if they're not moving, but they can still check your speed if they're moving.
How accurate is it?
I don't know. That's up to the courts to decide. Now what if we were dealing with an electron? So here's my electron. And my electron's traveling. Now what if I were to use my radar gun now? If I send out light, electrons have very little mass. They have a large wavelength compared to their size. When light strikes the electron, light's a wave, the electron is a wave, they're going to
Take
interact.
a smaller wave.
It's a smaller wave, but still it's a big enough wave that when light and an electron meet, they will interact.
No, but doesn't that make it a smaller wave?
It depends. No, it shouldn't.
I thought two waves, like,
It depends if they're constructively interfering or destructively interfering.
so it could make it a way bigger wave.
Could. So what happens is the light wave will change the direction of the electron, and the light wave will bounce off at a different angle. So it changes the position of the electron.
Why is that?
Because of the particle or the wave nature of the electron. The two waves will interfere with each other. Or the other way you could think about it is the energy from the light is given to the electron and it changes its momentum. So as a result, with the electron, because it has so little mass, light changes the path of the electron. Therefore, you can't measure its position, because the act of measuring it changes it. Because some of the energy is transferred to the electron, changing its speed. So you couldn't use a radar gun to measure the speed of an electron, because by trying to measure it, you change its speed. And that is Heisenberg's uncertainty principle. There are a number of ways you can state it. Here's one way you can state it. You can never be certain of the position of the electron. You can only state the probable location. And this is where, Rachel, we come to Heisenberg's famous cat. Okay, this is how he tried to explain his principle to people. Okay, you've got a box. Inside the box, you hear a cat. Actually, that was Schrodinger's cat.
Yeah, Schrodinger.
Sorry, I'll take an error on that. Schrodinger's cat. So inside the box, you hear a cat. You think the cat's alive because you hear it going meow, 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 meow. Okay? But the only way to open the box is to take an axe and chop it in half. So you take an axe, you chop open the box, and lo and behold, the cat's dead.
You chopped it in half.
So how do you know whether or not the cat was really alive or not? The act of measuring destroys what you were trying to measure. It could have been the cat was already dead and there was just some sort of like sound machine inside the box going meow, meow, meow,
Well, you
meow,
could
meow.
just check for a sound machine.
Well, maybe the sound machine, by opening it up, was smashed in half, so you don't know if it was actually a functioning sound machine or a broken sound machine. But the point is, the act of measuring destroys what you were trying to measure. So you can't measure the position of the electron because by trying to measure it, you change its position. Now we can express the Heisenberg uncertainty principle in terms of mathematics.
Sean, did you add any seed?
My brother did like a couple months ago, get like 20 papers.
Since it's impossible to know the position and momentum of an electron with exact accuracy at the same time, here's the equation. Delta x times delta p is greater than or equal to h over 4 pi. That's the Heisenberg uncertainty principle. Delta x is the uncertainty in position.
4 pi.
4 pi.
So what?
The uncertainty in position is delta x. Delta p is the uncertainty in momentum. H is Planck's constant divided by 4 pi. Now remember that momentum is p times, or momentum is m times v. So you could also express this as delta x times m delta v is greater than or equal to h over 4 pi, where m would be your mass in kilograms, and delta v would be your uncertainty in velocity in meters per second. Now, for those of you who are going on in quantum chemistry, you might see this. You won't see this in our class, but sometimes they do Planck's constant with a little bar across that. That's the same as this. So if you ever see that, it means Planck's constant divided by 4 pi. But you won't see this in our class at all. That's, if you go on in college, I just sometimes think I should tell you some of the stuff that you might see down the road. So your homework for tonight is to work on that